Hello and welcome to our second lecture on quantum statistics. And last time we introduced a concept of bosons and fermions and the occupation numbers. And I explained you how to construct for non-interacting in quantum mechanics a multi-particle wave functions in terms of simple one particle wave functions. And what we would like to do now, we would like to reconsider our microcanonical ensemble, which we introduced earlier, based using this idea. So let me remind you that in the microcanonical ensemble of non-interacting, we now specify states. Previously, we just counted particles, but now we, instead of counting particles, individual particles, we specify occupation numbers of particular energy levels. And all these occupation numbers, they are equally probable in the microcanonical. So we impose two constraints on the total number of particles in the system and the total energy of the system, where index alpha labels the states or energy levels in our system. And we would like to understand what would be the most probable distribution of these occupation numbers in the thermodynamic. To do that, we actually need to first to discretize the system. So to count states in the discrete system. Maybe even if the energy spectrum is continuous, you know, that as we did in the microcanonical ensemble, we introduce small volumes in the phase space. So we would like to develop a similar set of ideas. So to count states, we divide now the whole spectrum of the system into discrete cells, I equal 1, 2, 3, which are shown here, okay? The occupation. Now we assume macroscopically each cell has the same energy EI. So macroscopically all states in the cell has the same energy. But still there can be many microscopic states for a particular cell, okay? And we will denote the number of states in the particular cell as GI. So microscopically, each cell contains a large number of states, okay? But macroscopically, this number of states is smaller now. So the energy of the states is approximately, this GI is called the cell degeneracy, okay? So let's go on. Because of coarse graining, the cell occupation numbers for a given Ni, they will in general correspond to more than one quantum mechanical state. And as before, we want to find the set Ni bar, which corresponds to the maximum number of quantum states. And this set we call the most probable set, and this set describes thermal activity. So with given cells and their degeneracies G1, G2, Gi, we need to find the number of ways to obtain a particular sequence of occupation numbers. So we assign particles into single particle quantum states without paying attention which particle goes to which cell. For example, these are different cells, and we don't actually pay attention to whether particle 1 goes to cell 1 or 2 or 3. We just count number of particles or occupation numbers in each cell, okay? So this already automatically introduces indistinguishability of particles, okay? Because our counting now is based not on individual parts, but on occupation numbers. Then, once we assign a sequence Ni, we can independently calculate, because all cells, they're occupied with occupied independently of each other, we can independently calculate the occupation of each cell, which will give us just the total number of ways to for each cell, we will denote Wj for J cell, and J is occupation numbers, is the number of ways and J particles into the J cell. And each cell, if you remember, it can contain GJ single particle states. Okay, so for each cell, for example, into cell J2 and 2 one particle states, and then Wj and J will be the number of ways to put all these particles into that cell. And then the total multiplicity will be obviously simply the product over all cells, because if we have the number of 5 ways to put particles here, 3 ways to put particles here, 4 ways to put particles here, then the total number, the total number of ways, so the total omega will be simply the multiplicity. It will be simply the product of 3 times 5 times 4, which will be equal to 6. Okay, and it will not distinguish particles. This counting only is based on the occupation numbers. So first we start this counting for fermions. Okay, for fermions, remember that each single particle state can accommodate at most one particle. So it means that each state is either occupied or, so if you take a cell number J with total GJ states, so to place NJ fermions into GJ states, we pick NG states out of total GJ states. And in this case, this individual multiplicity for this cell is simply given by a binomial coefficient. The number of ways to choose Nj out of Gj. And the total multiplicity for a given occupation, for a given sequence of occupation numbers will be given by this product. Now we want to take the thermodynamic limit such that in the thermodynamic limit, microscopically, remember that we assume that Gj, number of states in each cell, is still sufficiently large. So we assume both Nj and Gj large and use Stirling approximation to approximate factorials in this expression. When we take log, this is what we get. This is the expression in terms of occupation numbers and cell degenerates is Dj, sum of all possible. So the most probable distribution then for occupation numbers will be obtained by maximizing this expression subject to constraints on the total number of particles and energy. Okay, remember that the total number of particles is fixed, the total energy is fixed. So we need again to solve this problem using Lagrange multipliers method. And what we do, we take log of the multiplicity given in the previous slide, add two constraints with arbitrary coefficients alpha and beta, and then we, as in the Lagrange multipliers technique, we assume that now all Nj in this variation problem, they are not constrained. And so we can constrain them independently, and this result, taking the variation, small variation of this expression with respect to Nj, this result in this expression, and because all variations of occupation numbers are independent, we require the expression in the square brackets to be 0. This should give us the maximum of this multiplicity as a functions of all occupation numbers. So this is the equation we get, and if we solve it in terms of the occupation numbers, this is the most probable distribution of occupation numbers in this Fermi-Gas system, where Gj is self-degeneracy, which we don't know, but later on we'll see that they actually don't matter. And there is the denominator, which depends on two constants, alpha and beta, and we will determine these constants later on. Now, Fermi. Who was Fermi? Fermi was an Italian physicist who basically was the creator of the first nuclear reactor, the Chicago Fire. During the Second World War, he moved to US because his wife was Jewish, and as a result of the Nazis' policies to Jews, they were forced to move to US, and where he became a very famous physicist, and he excelled in both theoretical and experimental physics. So in 1938, he was awarded a Nobel Prize in Physics for his work on induced radioactivity and for the discovery of trans-uranium elements. He also made significant discoveries in the development of statistical physics, quantum field theory, and nuclear particles. When Pauli formulated his exclusion principle in 1925, Fermi followed with a paper in which he applied this principle to an ideal gas, employing a statistical formulation now known to us as Fermi-Dirac state. Fermi was also one of the fathers of neutrino, okay? And his theory, later referred to as Fermi interaction and now called weak interaction, it describes one of the four fundamental interactions in nature. After the war, he served under Oppenheimer on the General Advisory Committee and on nuclear matters, and later on he strongly opposed the development of a hydrogen bomb on both moral and technical grounds. Okay, he was quite a famous figure. Okay, so now once we derive the distribution for fermions of occupation numbers, let's move on to bosons. And for bosons, if you remember, the occupation numbers can take any integer number. So bosons can occupy the same quantum states as many times as you like. And to count particular multiplicity for a particular cell, for boson particles, we just use the same approach as I think you used in counting states in the Einstein solid model. So what basically we do, we want to place, because now we have Gj states in a particular cell J, and so Gj quantum states in this cell, and each quantum state can occupy as many, have as many quantum states what I mean that there are Gj quantum states in the cell, and particles can occupy any particular cell as many times as they like, okay? And how this counting is achieved? So here by circles we show particles, and we need which is the corresponding occupation number, and J, and we need to distribute these particles among Gj cells in any way we like, okay? And this can be achieved by taking Gj minus 1 partitions. For example, if we have 4 quantum states, then we can, this is one of the possible configurations. And in the state 1, 1 particle, in the state 2, 3 particles, in the state 3, no particles, in the state 3 particles. So what we basically do, moving these partitions, Gj minus 1 partitions, which divide all particles into Gj cells. We basically cover all situations when we place all particles among the cells. So, for example, if you move all partitions to the left, first 3 quantum states will be empty and all particles will be in the last quantum state. So moving them around, we basically cover all possibilities to distribute Nj particles among Gj cells. And to count the number of ways, we just need to count in how many ways we can choose. So if we now consider all these balls and partitions as on the same ground, we basically need to choose how many ways to choose Gj minus 1 objects out of total Nj plus Gj minus 1 objects. So total number of balls is Nj, total number of walls Gj minus 1. So a number to place these walls among these balls is simply choosing Gj minus 1 object out of the total Ngj minus 1 object. And this is given by, again, by a binomial coefficient of this form. Okay, so this will be occupation number for a particular cell. Again, then the total multiplicity corresponding to a given sequence of occupation numbers will be given by this expression, product over all possible cells. And again, we take the limit n and j large, n and g large, approximated by the Stirling formula, and solve again our Lagrange multiplying variational problem. It looks all very similar to the Fermi case. We vary with respect to the occupation numbers independently, and this is the equation we get. And the only difference to the Fermi case, that in the Fermi case we have plus here, and in the Bose case we have minus here. So this is the most probable distribution of occupation numbers for Bose-Gar. Okay, who was Bose? Bose was an Indian physicist specializing in theoretical physics, who was best known for his work on quantum mechanics in the early 1920s, and he provided foundation for Bose-Einstein and the theory of the Bose-Einstein quantum. He actually was nominated several times, 1 to 4 times, by his colleagues for the Nobel Prize in physics for his contribution to Bose-Einstein and the unified field theory. But he never got it. And Dirac actually wanted to just honor him for his achievements. And he suggested that the particles that obey Bose-Einstein would be called bosons, okay, after Bose. So this name was proposed by Dirac, and now Bose is known to us, very well known to us because of this name of particles with the Bose static. Okay, so let's look what we just derived. We derived the average occupation numbers in these quantum gases. Now this is quantum because our consideration were based on some consideration of quantum mechanical wave functions, and so we need to consider, I showed to you that we need to consider two cases. Fermi case, when occupation numbers can take only values 0 and 1. So on average, we will have this expression with +1. And in the Bose case, the sign is minus. Okay. We still have these two constants, alpha and beta, which we need to fix from the which we are going to fix from some classical arguments. The first constant we need to fix is from the total number of parts. Okay, because if this is the average occupation number for a particular cell J, then when we sum over all cells, this should give us the total number of particles. Now what I want to do, I want to go to the thermodynamic limit when the number of cells goes to infinity. In this case, we can replace the sum over all cells in the system by a sum over all states. Okay, and this will automatically take into account this cell degeneracy. Remember, because as we define what any particular cell, we define a cell by its energy. So cells, they have energies indistinguishable at macroscopic levels, and the number of states in each cell with the same energy we denoted as Gj. Assuming that particles don't have any internal degrees of freedom, it's quite obvious that we can replace this sum over the all moment of particles. Because for a given momenta, for example, if we know the absolute value of the momentum of the particle, then we know the energy. Because in this case, if we know the absolute value of the momentum, the energy is given by this. So the energy is fixed, but we still have all possible directions of the wave vector or the momentum, and it will count exactly for this cell degeneracy in the discrete sense. So when we take a continuous limit, we can simply replace the sum over energy cells with the degeneracies by the sum over the wave vectors of particles, and this will automatically take into account the cell degeneracy. Okay, so in this limit, when we sum over all the cells, we can expect that the total number of particles now will be replaced, because the sum over energy cells is replaced by the sum of the wave vectors. This Gj is absorbed into the sum, and this is what remains, the denominator. So this is one constraint on the constant alpha and beta, that this sum should be equal to the total number. Okay. Now, let me remind you that in when we have a quantum mechanical system, for example, a particle in the box, if you have n particles in the box of the volume V, then we introduced a density, a small n. Okay, and assuming that volume V is say a cube of the size L, we can write it as 1 over L cubed, and we can write it in terms of the wave numbers corresponding to the linear size L. This wave number, when L goes to infinity, K goes to 0. This is basically, if you remember from quantum mechanics, if we have the wave with the number KL, then this is the minimum, the smallest Ka possible, or the largest length wave possible, and then we can fit in the box of size L with waves with wave numbers KL, 2KL, and etc. etc. So basically, the smallest wave number will just be like a half period of the sine function. The next one will be just wave function with over the full period, and etc. etc. So the higher M, more and more standing waves we can fix. Okay, so this is how we go from the volume to the wave numbers. Now, in this thermodynamic limit, if we take this quantity, the density, and take the thermodynamic limit, this can be replaced, the density, by the integral over the wave numbers in three-dimensional space of wave numbers, and in spherical coordinates, this integral becomes, okay? Actually, I wrote some notes about making this limit, and let me probably comment on that and explain it in a bit more detail. So now I will stop sharing this file and share another screen, this one. So the problem: show that in thermodynamic limit, any quantity f, any function of energy states or cells, when we sum over all cells in the energy spectrum with corresponding cell degeneracies, goes to this integral v over 2 pi squared integral of this function, depending on epsilon k and the integral of the absolute values of the wave number. How we do that? Let me remind you that the energy of any particle is related to its wave number by this relation, and the momentum of the particle is related a reduced Planck constant times its wave number. So, as I just explained before, the sum over all cells, energy cells in the spectrum, with corresponding degeneracies, can be replaced by the sum over all wave numbers, okay, k, where k, once we fix the absolute value of k, we fix the energy, and this corresponds to a particular energy cell, but all possible direction of the vector k, they correspond to this self-degeneracy. So if we have, so this is what we expect in the thermodynamic limit. If you have a system of volume V, then each state, we know from quantum mechanics, takes the volume delta x delta p over h. This is the elementary linear size it can take. And we take a cube of that. This is the elementary volume occupied by any quantum particle. So if we remember now this relation that P equals hk, we can substitute in the thermodynamic limit delta P delta x by delta x delta k, and there is an extra factor h here. So we get an extra factor h reduced Planck, a cube of it, or a cube over the h cube. This gives us an extra factor 1 over 2 pi cube. Okay, so I just shown that the sum over the state energy cells in the thermodynamic limit, it goes to the integral over the volume and integral over the all wave vector. Now, if our function does not depend on the coordinates, in the case of homogeneous system, and depends only on the energy, integral over the volume becomes V, and integral over the three-dimensional space of wave numbers, we can calculate in spherical coordinates. So this is what we get, and that 2 pi cube comes from here, and this is the angular integral is the area of the two-dimensional sphere, which is equal to 4 pi. And if we collect it all together, this 4 pi cancels 4 pi here, and what we get v over 2 pi squared integral, one-dimensional integral over the absolute values of wave numbers. Okay. In particular, if we take the average number of particles in the system, which is given by this expression, then using this formula, we get this expression, integral of the wave numbers. And so dividing by the volume, we get the expression for the density in the thermodynamic limit in terms of occupation. This is what I showed you in lecture notes. Okay. So let's go back to our lecture, share. This is basically was this relation for the density in terms of this integral. Now in this integral goes over k here. Let's make a change of variables. Let's remember that the energy of the particle, where is it, is given in terms of the wave number by this relation. This is Ek. So if we now introduce another variable x using this relation and express k as a function of x using the previous relation of Ek in terms of k and make a change of variables, this is what we get for density here. Some prefactor, which depends on the constant beta, which we still don't know, and the integral, which involves integral over some abstract variable x, which involves another unknown constant. So this should be a density of our system in thermodynamics. Okay. So this is the expression for the density. Now let's see what happens when temperature goes large. So when temperature becomes large in the high temperature limit, beta should go to 0. Okay, because in this limit, what happens? Yeah, I'll talk about this a bit later. So in the high temperature limit, we expect beta to go to 0. This because so let's assume that in the high temperature limit, beta goes to 0. Okay, so if this goes to 0, then the density will become very high. So the only possibility that if this is 0, this guy should go to infinity. So exponential of minus alpha should become very large. So if this becomes large, then we can discard this plus minus 1. And in this limit, the integral will give us just some constant. So in this limit, beta goes to 0 and alpha goes to minus infinity. Then in this, when exponential of minus alpha becomes large, then the this particular occupation numbers. So this in this limit, we will get a finite density. So and what we expect to have the Maxwell-Boltzmann distribution, because a difference between bosons and fermions will disappear. So this occupation number, where is that? Nk. This is this is occupation numbers. Did I put it? Okay, we expect that occupation numbers in this limit, they I need to use this original. Yeah, this is the expression, which is this is the expression for the occupation numbers. The expression for the occupation numbers. We expect that when beta is small, alpha is exponential of minus alpha is large, then we can neglect this guy, and we expect that this occupation numbers will go to the Maxwell-Boltzmann distribution. And this is exactly, it becomes alpha in the Dimiret minus beta epsilon k. Okay, so if you want to identify it with the Maxwell-Boltzmann distribution, so we must choose beta to be is 1. So at high temperatures, Bose and Fermi distributions, they approach classical distribution because occupation numbers become very small. So what about this parameter alpha? For the parameter alpha, we will introduce a notation z, exponential of it, which is called fugacity, which we call fugacity, and we can introduce the chemical potential as log of z over beta. Still, at this stage, this Z and introduced in terms of alpha and this mu introduced in terms of Z, they are still formal variables. But later on, I will show you that in the classical limit, in the high temperature limit, they will exactly match the definition of the chemical. So if I now write down this expression for density in terms of this parameter Z and beta equal to this, I can combine this prefactor. In fact, it can be combined into the thermal wavelengths, if you remember the definition of the thermal wavelengths, and the resulting expression for the density in terms of the thermal wavelengths, this becomes this expression, okay? Where Z is this fugacity and occupation numbers for a particular wave vector, they are given by this expression with +1 for fermions and -1 for bosons. Okay, now we want to derive the equation of state for these quantum gases. And to do that, we need to find the pressure of the quantum ideal gas. And for that, we need to calculate a momentum distribution function, if you remember, which we introduced for classical gases. And we introduced the momentum distribution function for homogeneous gases as that if we integrate it over all coordinates and over all momenta, we get the total number of particles. If we compare it with our definition of occupation numbers for a given momentum of the particle, occupation numbers, they depend only on the value of the momentum, okay? And then we integrate over all elementary cells in the phase space. Then we can immediately see a relation between the distribution function and the occupation number is given by this relation, okay? We use this distribution function previously when we talked about classical gases. So this is the distribution function in terms of the occupation numbers. And to calculate pressure, we can use exactly the same formula as we did when we calculate the pressure on the wall for for classical gases. So the pressure, the expression for the pressure, if you don't remember how we did it, just please review it. And so it was given by the integral over the momentum space, kinetic energy mv squared over 2 kinetic energy over 3, and with the distribution function. But now instead of the distribution function here, we substitute its expression in terms of the quantum occupation numbers for bosons or fermions. And when we do that, we get this expression for pressure. Okay, so this is basically the same integral with the occupation numbers substituted. This is mv squared becomes the energy of the particle. This is the occupation number. And this is the three-dimensional integral over the all possible in the space of phase. Okay. Again, we do the same change of variables as we did on the previous slide, changing the integration variables. This is a three-dimensional integral which we reduce to the one-dimensional integral over the absolute values of the wave numbers, and we take this change of variable, introduce lambda as the thermal length again, and what we get for the pressure over kT is the following expression in terms of the thermal length and the fugacity. So now we have 4 quantities here: pressure over temperature, thermal length, and fugacity. And this is just some formal integral. Okay. Now we can also calculate the internal energy in this system. So you see that this is not. It doesn't look like the ideal gas law for the pressure system, because out of here we calculated the ideal gas law. It looks nothing like that. But if we calculate the energy of this quantum Bose Fermi gases by basically summing again over all momentum space or the occupation numbers multiplied by the energy. When there was no energy here, it was a total number of particles, but now if you put energy here, this becomes the total energy of the system. Again, applying this the same trick to go to the integral, we get the volume times the integral given by the same. And if you compare the integral with the integral which we get in the pressure, this is exactly the same integral. Okay, so if we divide this expression by this expression, we get a universal relation. PV equal 2/3 of the internal energy. Okay, this was the relation for classical ideal gases. The same relation true for quantum ideal Fermi and Bose gases. So pressure, our pressure is expressed in terms of the internal energy. The only difference that for classical ideal gases, the expression for the internal energy was 3/2 kT, okay, times number of particles. And 3/2 cancels that 2/3, and we gain the classical ideal law, nkt. Now the internal energy is a much more complicated expression in terms of the temperature, beta enters here and etc. So this is now the internal energy for quantum gases. Okay, so I probably stop here. I need about 10-15 minutes to finish this subject, but I will continue next time.